And so now we know how to compute the green functions in the 5-4 theory. So for that, basically we need to know two formulas. One is this master formula that expresses the Green's function in terms of free fields. And then for free fields, we need to use the Wick statements. So this way of disentangling various terms then leads to Feynman diagrams, and this is just a nice graphic way to represent the result, or to organize the calculation in a nice way. So the Green's functions, well, they look a little bit artificial. It's just an object that we define, and it's not very clear what is it good for. Now I'll describe how to compute some quantities that are directly related to physics. So in quantum mechanics, as usual, we can only compute probabilities. So we're going to discuss how to compute probabilities of certain processes, namely scattering amplitudes. So quite often, the question that we want to, so the physical situation that we want to study consists in the following setup. So at some remote past, infinitely remote, in some approximation, we consider a system of particles that are so far apart that they don't interact at all. So and then they come closer to each other, interact, and produce other particles, which then fly apart to infinity. So at asymptotic infinities, we have free particles. Then there is some interaction region. And then the produced particles fly apart and become free again at equal plus infinity. So the typical example is of applications of this type of this setup is well, experiments in particle accelerators, where they collide two bunches of say protons, and then they measure what is produced, what particles are being produced. But this is not the only place where this is useful. For instance, in kinetic theory, one quite often uses the same setup, although of course the time between collisions there is not infinite, but the interaction between particles in a gas or in plasma, there is, I mean, the time during which particles interact is much shorter than the time between the collisions, and so one can, so as a first approximation, or one can actually consider particles as almost all the time being free, and then describe interactions as if the time interval between the interactions was infinite. So how to set up this problem in quantum field theory? Well, this means that in the infinite past, we have some state which is just a state with n particles. And then in the in the infinite future, we have another state, which is so also a state of particles, but in general they will have, well, the particles can be produced and destroyed. So the number of particles need not be conserved, and well, of course their momentum will also be different. So the in state is given, and we want to calculate the probability, the probability to produce a given out state. So presumably, so this probability, if you know how particles interact, this probability should be calculable. So the out state, of course, is related to the in state linearly. There's some operator that describes this infinite time evolution. This operator is called the S matrix, or scattering matrix. And so basically this is evolution operator e to the minus I h t with infinite t. So the amplitude, the probability amplitude of this process then will be equal to the matrix element of the S matrix between the in and out states. Yes?
So can you call a probability amplitude, but what precisely does it signify?
Just as usual, the square of it is the probability to find the out state. Sorry? Yeah, to produce a particular out state from a given in state. Okay, so let me give you the formula for this amplitude. Again, I will not derive it, but it should be more or less obvious from the construction of the Green's functions that the operator that this evolution operator is a time-ordered exponential of the interaction Lagrangian. So this formula allows you to calculate any amplitude in principle, because okay, so the direction Lagrangian is built from free fields. They are linear combinations of oscillators, and the external states are also made of oscillators. So at the end, the problem again reduces to commuting the ladder operators. And so there is also a shortcut way to represent this in terms of Feynman diagrams. So the only new ingredient is that we need to introduce contractions of external particles with the fields that arise from interactions. So this well, again, this contractions are just commutators of phi plus or phi minus with A and A dagger. And let me just give you the answer. So the contraction of the field phi with the particle in the in state is equal to the wave function of this particle. So it's e to the minus itx. So this is in the coordinate representation. And when we go to the momentum representation, this just becomes a 1. So for a particle in the out state, the contraction with phi of x is the conjugate of the wave function. And again, this becomes 1 in the momentum representation. Yes?
So in our formula for the scattering amplitude, it's like the scattering amplitude equals the interacting field Green's function that corresponds to the sort of inner function 1. As in time ordering, there's an inner function, and then in the master formula, there's the exponential. Why should that inner function be 1?
Let's say, so in the Green's function, we start with some fields. And then we, so the exponential describes their, they evolve with the interacting Hamiltonian. And so that's why this exponential arises. So here we start with, so there's, in the middle, the system evolves, what should I say? That there are no other sources of interaction. There's only, well, directions between particles described by the interaction Lagrangian, and the only input comes at plus and minus infinity, so in the external states. That's why there is nothing in between. So the only input is in this in and out states. Yes.
You mind why you put what is this called?
What is what? This is contraction.
Yeah.
So you compute these matrix elements using Wick's theorem, commuting oscillators from left to right. And so each time you commute two objects, like if you commute the field with an oscillator that creates the external state. So, for instance, what is the external state? The out state is just, well, it's a product. You just take oscillators and create all these particles. Okay? So, well, there's a bunch of oscillators. So to compute the matrix element, you need to pull them through all the field operators to the left. And they'll pick up contractions when each time you commute them through the phi. And so this contraction is just the wave function, which is very easy to derive. So now we can formulate this in terms of Feynman rules, just graphically. And it is convenient to do it for the T matrix. So one can write S as the unit operator plus IT, where, well, this corresponds to just a trivial process of nothing happening. Particles just pass through each other without interaction. And T describes the non-trivial processes that can change the characteristics of the external states. So the probability of something to happen would be determined by the T. And then we can formulate Feynman rules how to compute the matrix elements of this operator. So this will be given by the sum over all possible diagrams. So each incoming particle corresponds to an external leg in the Feynman diagram. So the interior of the diagram will be built out of vertices and propagators. And then we will have outgoing lines that correspond to the produced particles. And in the momentum space, the external lines don't carry any factors. Okay, so because the convection is just given by 1. So in other words, the Feynman rules for the amplitudes are essentially the same as for the Green's functions. The only thing one should do is one should amputate external legs from the Green's function. So throw away all the factors associated with external lines. So in a sense, amplitudes are equal to connected part of the Green's function. With external legs amputated. So let me give you an example. This is the simplest calculation one can do in field theory. Yes?
So, the Feynman diagram, you just sandwich the identifications in outstanding.
You can also draw a Feynman diagram, but this would be a very trivial diagram, right? So you will have lines that connect. So that then the in and out states should be the same. So you connect each particle to the initial state to the final state. The total factor will be 1, right? So it's just.
So how to connect this? Just
Let me maybe go through this example to become more clear. So let's compute two scattering amplitude. In pi4 theory. So we have already studied the 4-point Green's function in this theory, and 2 scattering amplitude is just the same Green's function with the external legs amputated, and we should only keep the connected piece. So as we learned yesterday, then, okay, so we want to study the transition from state with two particles that belong at P1, P2, to state with different momenta. And so to the leading order, this is described by one single diagram with an interaction vertex in the middle. Now, for the Green's function, these ends were all propagators. So the coefficient function, analytic expression associated with this diagram was a product of 4 propagators times the interaction constant in the middle. Now what we do is just drop these factors. And then what remains is simply the factor of minus I lambda associated with the vertex in the middle. And in principle, we should also write the momentum conserving delta function. So the momenta here, they have directions. So their initial momenta pi1 and pi2. And then there are final momenta pi1 prime, p1 prime, p2 prime. So the only dependence on momenta here appears in the delta function. But this is just because this is a very simple example. This is not generic. The appearance of this delta function, though, is generic. So whatever amplitude you calculate, it will be multiplied by such a delta function just because of energy and momentum conservation. And, well, the Feynman rules are consistent with the conservation laws. So this will always appear. So oftentimes, what is called the amplitude is the coefficient in front. So oftentimes okay, so let me write it for a general state. So we can always write this as I times m, which describes transition from m particles to n particles, and then 2 pi to the 4 times the delta function of the momentum conservation. So it is often, this coefficient is called the amplitude. So in our example, this amplitude is just a number. So in pi4 theory, we thus conclude that 2 to 2 amplitude is given by minus lambda. Well, of course, there are other diagrams at higher orders, so there will be corrections which are suppressed by the coupling constant. So, well, to the first approximation, that's all what you need to know about filtering. So that's it. I could have finished here. But since there is almost another week to go, I will continue with applications of this to some physically interesting theories. Yes?
Why the only connected diagram contribute to?
Yeah, so I wanted to avoid answering this question, but since you asked, yes, so there is a, well, the physical reason for that is that if you have two disconnected parts in the diagram, they describe just sub-processes of scattering of, subsets of particles. And so one could have included them, but the really what we are, if we are studying, say, a process of 2 particles going to 4 particles, experiment, then we don't want to include as a sub-process so suppose we want to study 2 to 4 process. So potentially this can arise in 2 ways. So one way is when these particles scatter, producing 4 particles. But there is a possibility that, so if these particles are unstable, they can just decay pairwise. Now this, of course, can happen without these particles coming. So they can still be separated by macroscopic distances for this to happen. So this is in some experimental setup. This would look very differently from this process. And so in the calculation, we want to separate these 2 cases and do not include the probability of this when we calculate the probability of real scattering when all of the constituents interact. So therefore, we should keep only connected diagrams. Yes?
So do you mean that in the second process actually is 2, 1 to 2 process? In the second.
Yes, this is just
this
2.
Is why you excluded this.
Right. So also the probability of this process will be much bigger than probability of that process, because this decay can happen anywhere in space and time. And so this will be proportional to the volume of, well, of the whole space, or at least on the portion of space where the wave functions of these particles are localized, times the interval of measurement squared, because there are 2 particles here. This process will be proportional to this same volume factors, but to the linear power. So this is much, in a sense, is a much bigger probability. So one wants to separate this from that. Yes?
So, are you saying that this process will be described within the identity part? Is that what you're saying? Or
Not really, because this still contains interactions. But we want to study reducible processes. So and that we can separate using diagrams. So it is possible at the level of the diagram to separate this interaction that involves all the particles in the initial finite state from these sub-processes. Yes?
So when you say amputate the external legs, do you mean draw a diagram that's the same as that diagram, but in which the external legs end on external points, and then write the momentum space expression that corresponds to that second diagram, and then just take the coefficients in that diagram?
Yes, absolutely. So, right, so in all of these diagrams, so let me draw this diagram, for instance, in more detail. In fact, in 5-4 theory, only this diagram would be possible. So in this diagram, this factor would correspond to 1. This would be 1. This would be 1. This would be 1. This would be 1. and this would be 1. But this vector would be a propagator, and this would be a propagator. So this will be d of some momentum that goes through this line. And this vector will be the real propagator. Because these are internal lines, and these are just signify the particles that come in and out of the interaction region. Any more questions?
Just when I hear amplitude lag, it means we completely get rid of it as an erase it, basically. But instead
Basically
we're
erase,
doing-
yes, but you need to know how much particles were in the final and the initial state, so we still draw a line. But there is a factor 1 associated with it. So in the Green's function, this would be also really a propagator.
So, yeah, it seems to me that in the example, instead of erasing the external lines, we had each external leg end on an external point.
Yes?
So we're not really erasing it?
Okay, so let's compare the Green's function that we computed last time. So this was given by the diagram of this form. So this was x1, x2, x3, x4. And so this was, the integral over, so when we wrote it in the momentum space, I don't remember if I've written this in space, but anyway, in momentum space, this would be the integral over, so this will be momentum P1, P2, P3, P4. So this will be the integral over P4, P1, P4, P2, P4, P3, P4, P4, times the propagator that corresponds to each of these lines, P1 squared minus m squared, I over P2 squared minus m squared, I over P3 squared minus m squared, I over P4 squared minus m squared, times the vertex, which is minus I lambda 2 pi 4 delta of P1 plus P2 minus P3 minus P4. So in the, and so this should be also multiplied by e to the I P1 x1 plus I P2 x2 minus P3 x3 minus P4 x4. So in the amplitude, all of this would be absent, because all of these factors correspond to external lines. So we just eliminate the external, the propagators that associated with each of these lines are not present. There is no integration over this momentum, they just given. And so what's left is the vertex and the delta function. I suggest to make a break now for like 3 minutes or so.